Hey everyone, welcome to this special edition of the Pickup Show, the show where the algorithms are always accurate. I am your host, Professor Roos, and in this episode I'm going to show you how to do some basic iterative calculations in Google Sheets. Our goal here is to not only show some iterative calculations and a couple ways to do it, but to build what I like to call a kinematic problem solver. All right, let's get to it. If you haven't already, fire up a version of Google Sheets, and you'll notice that I've already built a control panel here. If you haven't watched the control panel video, you might want to start there and get this built before you join in and follow along. I added a couple things here. I color coded it and centered things to make it look kind of nice. I also added some wording and some unit labels to it. That way, if anybody looks at this, they'll know exactly what X naught, B naught, and A are. This is akin to commenting your code in a real programming language. Just good practice to get into. All right, so our goal here is we're going to make three columns. We're going to have a time column, a position column, and a velocity column. All right, and I'm going to highlight these and center things. I like to make things look nice and neat. You don't have to do that. It doesn't really change the functionality or anything, but it centers things. All right, so what we're going to do, I'm going to start out underneath the time column. Each successive row here, each successive cell will have a different time, and I want the times to be separated by a specific amount of time, a time interval that I haven't defined yet. We'll do that in a moment. But we're going to start out at time 0. That's usually where we start observing things. At the instantaneous time is time 0. And let's say that we wanted to make some observations and predict using the kinematic equations for position, the famous 1/2 AT squared, and the kinematic equation for velocity. We want to predict what's going to happen to something subject to a constant acceleration for different times. Right? So that's what the position and the velocity columns are going to be. We're simply going to use the kinematic equations, evaluate them at the time which shows up in each successive row. So first of all, let's populate the times. Now what I could do, let's say I wanted to evaluate the position and velocity at every 2 seconds. So I could just start typing in here. Right? Just type in a value, hit enter. If I want to go down to a significant amount of time, you could type this, but anything more than 20-30 seconds, you're going to get tired of typing. Right? So there's got to be a way to automate this, and that's the plan to show you how to do this iteratively. Right, so what I'm going to do, highlight the box or the cell right below 0. Now this is where I want it to be one time interval later. So let's first of all define our time interval. So let's go over to the control panel. This is a time interval. That's all it is. It's not playing the role of anything else other than separating our times in the time column. All right, so I'm going to call this dt. Don't get confused. Don't confuse this little dt. That's not an infinitesimally small quantity. I'm just not going to go in and call it a capital an uppercase delta t. So this is a time interval, and here is where I have to define it. So there's a few ways to do that. Again, watch the control panel video, but I'm going to come up here to the name box, type dt, hit enter, and so any value I put here will be associated with dt. Let's make it look nice and give it the same color here. I don't remember what color that was. This one maybe? Yeah, it doesn't matter. And let's call it, say, 2 seconds. All right, so go to the cell right below the initial time, and here's how we're going to program this. I'm going to let this box equal the previous time, which is the box above. So I simply select the box above, and look, it kind of color codes things for me. This turns orange, and it turns the same essential background color as this, plus, now it's going to be dt, and look, it's a little harder to see because that's kind of a, I don't know, a brown color or something, but it colored it changed the color of the lettering dt to the background. It matched the background of the location of the value of the name dt. Right, so if I hit enter, then indeed I got 2 seconds later here. So you might say, well, what have you gained? Do you have to type that in every time? The answer is no. If you go back to what you just programmed, and notice this, see this little box here? There's the cell is outlined, but now look at that little square. See that in the lower right? If I put my arrow over it, it turns into a little plus sign. What I'm going to do is do a left click drag. Left click, drag it down and let go. And there's this smart feature where it tries to guess what you want it to do, and it guesses correctly in this case. What it does is it simply adds delta t to each previous box to create the new value. So if you want to see, just to check one of them, let's double click on this one here. So highlight it, do a double click, and it shows you the formula that was used to get this value. Sorry, it's using the value of the previous box, previous time, E6, plus that constant dt. So it is indeed adding 2 seconds dt to each successive, each previous value. Now, let's say I wanted to go down to, I wanted more than just 16 seconds. Well, you can do the drag down. You can also just pick up where you left off. So go hover over that little box, left click drag, and you can go thousands of values if you want. You may or may not need thousands of values, but if you need to, it can do it very easily. So I'm just holding my cursor all the way down. I'm still left click, and you can see on the left hand side things are counting up. And we've got hundreds of values now. Let's stop in the neighborhood of 1,000. Again, we may or may not need that many, but let's just stop right about there. Okay. I think this might, I think you can actually tell it if you want more than 1,000 here. You can tell it, add more rows at the bottom, and it will do it automatically for you. All right, so let's go back up. So I scrolled back up here. So that's, we've populated the time here, right? And excuse me. Let's see. Like I said, our plan is to now populate the value, the cells underneath position and velocity, simply by taking the adjacent time and shoving it into the kinematic equation. So let's do that. Let's program the position first. So this is the famous half at squared equation. So this is equal to x underscore 0. Now you'll notice as I type these out, every time it recognizes that it's using the value of one of the defined parameters, it's going to color coordinate things for me like it just did here, and the same background over here where that value is located. Very useful. Plus v 0, right? So it's using that funny looking brown again, times, now remember, I want to choose the time from the time column. I want to choose this adjacent time. Remember, dt here only plays the role of separating the individual times that we want to use in the equations. So I got to just come over here and click that box there. Everything is color coded here, so it makes E2 blue and it shows you what you've just chosen. Okay, plus I'll use 0.5 instead of a half times A. So now it should have recognized, so it's got a little matched this background for A with whatever that is, sort of, I don't know, kind of a brownish reddish color, times, and now it's got to be t squared. So I choose the same time, that same box E2, upward pointing arrow 2. Don't forget to square it. Look closely, make sure that's exactly what you want it to do. It looks like it is. And of course we're going to get 0 for the initial position once I hit enter, because time is 0. I'm using the 0 time. But look what we can do. You can actually grab this, do that little drag down, left click, drag it just a few, and it populates things for me. All right. Now let me show you another way to once you've got one column dragged down. Let's get rid of this stuff. All right, and go back to what we just programmed. And before I do this, by the way, we probably, if we're going to do this calculation, you can see what parameters I'm using. V0 is 10. If A is negative 9.8, this is like a free fall problem. So maybe we're tossing something into the air at this speed. We want to know what happens relative to the origin 0. So we're tossing it upward. acceleration due to gravity is downward. Let's get a little more resolution on our time once we evaluate these equations. In other words, let's make it 0.1 second. And you can see that everything in the time column instantaneously changes to reflect the new value of dt. We can even go more resolution, maybe 0.01. Okay, or you can go to whatever you want. If you go to too small, you're going to have to drag down to more rows to get any significant amount of time out, of course. All right, well, let's go back to here. Now this has been programmed already. If you need to look at it, you can either see it in this field here, or just go back to the box and do a double click, and it actually shows you what you programmed that value to be. So go back to the one that's been programmed. Now again, you could drag this down the 1,000 rows or so, or here's another way to get it to do it. As long as this is adjacent to a column that's already been dragged down further, hover over, make that arrow turn into the plus sign, and do a double click, and it will automatically populate the values below all the way down to where we left off, and you can test that by going down here. And again, I think if you want more, you just highlight the columns and you can tell it to go further there. All right, let's program the velocity in. This will be easy to do. This equals v0. Again, the color matching should be happening, plus a times, oops, that's not correct, a times this time. I almost put dt in there. Right? I actually don't want dt, I want the time. I want that adjacent time, because that's what I'm doing. I'm evaluating the kinematic equations at that time. All right, so you get that, and let's do the double click again. Hover over there, do a double click, and it will iterate all the way down and match the highest row calculated so far. All right, so this is how you do some basic iterations in a spreadsheet. And now let's just do something interesting with it before we close. Let's create a problem, and this is why I call it the kinematic problem solver. I had my students build this and use this for years. You can solve just about any of those classic kinematic problems with this, or building something add on to it if you have more than one object involved. It's pretty easy to do, but let's just do a free fall problem, for instance. Let's say we've got a free fall, and I toss it into the air at 10 meters per second. This is close to the surface of the Earth, neglecting air resistance, of course. This is the acceleration due to gravity. Let's say we want to find the time it takes to reach its highest position, and what is that highest position. Well, you've got everything calculated here, and it's just a matter of scrolling down and observing, inspecting the position column for the maximum value. So let's see here, still going up, and yeah, still going up. I forget what number it hits here. Still going up. And somewhere here, isn't this exciting? There we go. We're somewhere in the neighborhood of 5.1 meters, depending on how accurate your value of the acceleration due to gravity is, but somewhere around here, looks like that's the max. Right? And of course you can tell what's happening. So I'd say about 1.02. If you want more significant figures or more resolution in the time, you can go to thousandths. You can get maybe a thousandth time in the thousandth space place where it reaches the max. But it reaches the max around 5.1 and a little more meters. You can see where the velocity changes from positive to negative here. So everything's consistent. So 5 meters at about 1.02 seconds. Let's say we're on the moon. Now let's do the same thing on the moon. Of course, on the moon it's exact. We don't have to worry about air resistance there. So about 1/6 of that is 1.6 or so. And notice as I changed the acceleration due to gravity, the smaller value, everything instantaneously changed. Again, that's why this is called the control panel. And now if we do this, I think it's going to be in the neighborhood of about 30 meters or so, if I remember right. And so let's go down, and somewhere around here, a little higher, right? Somewhere 22. We're close. somewhere around there. Looks like right there, right? Or you can see where it went, where it stopped, turned around from positive to negative velocity. So about 6.25 seconds, and you can toss that up to about 30 meters on. I always thought it'd be cool to have a game of hoops on the moon. Wouldn't that be cool? It'd probably be a dunk fest, and then you'd have to raise the rim. But then it'd only be dunking because there's no way you could have accurate shooting from at a 60-foot rim or something like that. All right, that is a demonstration of iterations in a spreadsheet as well as the kinematic problem solver.